Good morning, everyone. Today, I would like to ask you a question. How many of you have parked your car this week? Probably most of us. Now, here's another question. Have you ever wondered why parking spaces are the size they are? Why are some parking lots easy to drive through while others are very, very frustrating? Why are some spaces straight while others are angled? Who decided where every painted line should go? The answer is mathematics. Today, we are going to discover the hidden mathematics inside one of the most ordinary places we visit every week. As a matter of fact, every day, a parking lot. Let's begin. Starting with nothing. Okay. Suppose someone gives you a piece of land, then asks you to build a parking lot. Where do you begin? Do you immediately start painting parking spaces? Most likely not. Engineers always begin with one question: how can we use this land as efficiently as possible? Let's see how mathematics answered that question. Okay. So let's say we have a space like this. Okay. Empty land. How many cars can fit in this? At first, it sounds like a simple question, but it is not, because we don't just want to fit cars. We also need people to drive safely, walk safely, open their doors, find the entrances, leave the parking lot. So our real challenge becomes fit the greatest number of cars while keeping everything safe and efficient. This is called optimization. Okay. Optimization is one of the most useful ideas in mathematics. Okay. So let's go into the actual building of a parking lot. Okay. Let's get this space here. Let's draw an horizontal line to divide the space. Okay. And this is called driving lane. Okay. And this is where the cars move around. Without driving lanes, no one could reach a parking space. Now let's add the parking spaces. Okay. So okay. The goal of the engineer again is to maximize cars, safe driving, easy walking, and traffic, good traffic flow, to name a few that the engineer should consider. Now, something interesting we start to see. These goals don't always agree with one another. If we try to optimize the number of cars, let's say maximum number of cars you want to have, people may have trouble driving. If we make driving very easy, okay, we may lose parking spaces. Engineering is often about finding the best balance. Okay, so let's zoom into the actual parking space. Okay, on average in the US, a parking space is about 18 feet by 9 feet. So for a total of 162 square feet. Okay. Now, does a car actually uses all the 162 square feet? No. Our average vehicle in the US is about 15 feet long by 6 feet wide. So about 90 square feet. Okay. Versus the 18 by 9, which is 162. Okay. So you have a difference of about 72 square feet. And let's redraw the 18 by 9. Again, this is not to scale. So 18 feet by 9 feet. And then inside that, we have a vehicle, which has a footprint of about 90 square feet. So what happens to the rest of this? Whatever is left there, is it wasted? Did the engineer just waste 72 square feet? No, that space has a purpose. Its main purpose is to allow you to open doors, get children in and out, carry grocery, walk around the vehicle, reverse without hitting another car, and so forth. So that empty space, let's say the 72 square feet, is not empty. It's a working space. Without it, parking lots simply wouldn't function. So we've only designed one parking space, but a real parking lot may have hundreds or even thousands of them. The next question becomes, how do engineers arrange hundreds of spaces to fit as many cars as possible? That's where geometry takes over. So let's draw some parking rows. Okay. 1, 2, 3, 4, 5, 6. Okay. So we have 1, 2, 3, 4, 5, 6. These are 6 parking rows. Okay. If we continue with that same rationale, okay, I'll speed up this process for you. So we have here a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay. Now, let's double the lot. Okay. Instead of having only what 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 24 spaces, let's double that to 48 and so forth. Now, can we simply keep adding rows forever? No, because we are first limited by space. We don't have an infinite space to work with to build our parking lot. We need to factor in trees, sidewalk, lights, entrances and exits. Okay. So everything occupies some space. Every decision changes capacity. Okay. So let's go into the geometry of parking spaces themselves. Okay. Usually we have spaces like this, but all will depend again on the land or the space that is available to the engineer to build his parking space. So all these are 90-degree angles. You see, it's straight. Okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's about 5 times 3 is 15. So 15 spaces. Okay. Notice that each parking is perpendicular to the other. This is a 90-degree parking space. Okay. Why would the engineer choose this design? Because is it easier to park? Most drivers will say no. You usually need a turn to park in this space. Okay. Now let's look at another option. There are multiple options, but we are going to look at, for the sake of this video, at another option, which is a 45-degree angle. Okay. And traffic is flowing that way. So you have spaces like this in a 45-degree angle. One, two, three, four. That's about 12 spaces. So in conclusion, 90-degree spaces give the driver, first of all, it gives the engineer more parking spaces, but it is harder to park because sometimes you have to back up and move forward and all that. And as we know, a lot of accidents happen during this process. On the 45-degree angle, it's easier to enter, better traffic flow, and usually fewer parking spaces. Now, which design is better? Neither. All will depend on the goal of the engineer, the land space or the space that he's using, the requirements of the person who owns the parking space. There are a lot of factors. It depends on the goal again. The engineering, that's an engineering trade-off. We have to discuss what needs to be done and what is needed. Now, let's attack the occupancy mathematics. So 400 spaces, let's say 400 parking spaces. Suppose today the lot is about 75% full. So how much is that? How many cars do we have parked? So it's going to be 400 multiplied by 75%. That's about 300 cars that are actually occupying the space. So 400 minus 300 is about 100 cars. 100 empty spaces. We have 100 empty spaces. So now you try. If we have 400 spaces at 90% occupancy, how much is that going to be? Okay, you can pause the video and calculate that quick. So we have 400 multiplied by 0.9. Okay, that's about 360 cars or vehicles occupying. Okay, so for and on that for 400 spaces minus 360, so you have about 40 cars, 40 empty spaces. I'm saying 40 cars, 40 empty spaces. Let's say this is a parking space. We are going to make it a little simple this time. Okay. Then we have another row here. Another row here. And the store is here. Okay. We have one car here. Which is about 600 feet from the store. Okay. And another car here, or this is about 600 feet, 300 feet, 100 feet. Okay. So if the car is parked at 600 feet and another one is at 300 feet, walking speed is about 4 feet per second. Okay. So 300 feet divided by 4 is roughly about 75 seconds. Okay. 600 feet divided by 4 is about 150 seconds. Okay. Now, would you rather walk 1 extra minute or spend 5 minutes driving around searching for a closest parking space? Sometimes the best parking space is in the closest one. But again, everybody got their mind on this question. Some people rather stay there, wait for somebody to move out and park there, rather than saving minutes or a minute going there on an empty space that is about 600 feet away and park there and then just walk to the store. But again, this is just a personal stuff. Now, I want you to become an engineer for a minute. This is the space. Okay. Your challenge is to have 100 cars, to factor in safe traffic, factor in entrances, exits, sidewalks, accessible parkings, trees, lights, drainage, and so forth. There is no perfect answer, as you know, to this question. Everything is relative to the place or the space that you have and what is the requirement for the person who actually owns the space or want to use the space. Okay. So what did we learn today? We learned optimization, geometry, area, measurement, percentages, estimation, engineering. We just didn't study parking lots today, we studied mathematics. Parking lots were simply our classroom. Today we discovered the parking lots are much more than painted lines. Okay? Every parking space, every driving lane, every entrance, every exit, every sidewalk, every tree exits because somebody used mathematics to solve a real world problem. The next time you park your car, don't just grab your keys and walk away. Take a minute to look around. You will realize you are standing inside one of the largest everyday mathematics problems you'll ever encounter. And that's exactly what this series is about, showing that mathematics isn't hidden inside textbooks, it's hidden all around us. If you enjoyed today's investigation, please like this video, subscribe to Scitame Learning, and share it with someone who thinks mathematics has nothing to do with everyday life. I'll see you next time when we uncover the mathematics hiding in another ordinary object. Until then, keep looking for the math that's all around you.